Okay. In the device diagnosis panel, the first function is the device health diagnosis function. This function is based on measuring the zinc oxide layer condition. Because the zinc oxide layer is vital in our device, when the microfluidic chamber engaged, the solvent and the DI water inside of the chamber, which can dissolve the zinc oxide layer or etch the zinc oxide layer, make it porous. So if the zinc oxide layer have been damaged, we can measure the extent of the damage by measuring the first order love wave resonance peak without any liquid contact. So here we show this device, the zinc oxide layer left as 97%, which means this device is fairly new, so it's trustable for the measurement. But if we replaced it to another device, which is the device we purposely etched all the zinc oxide layer on top, so you can see the result. If we connect this device without any zinc oxide layer, we can see the zinc oxide layer only have 1.13% left, which means this device almost dead because the guiding layer have been dissolved by the solvent in the microfluidic chamber. This switch it controls the device surface coverage analysis. I want to highlight this one because it's related to a very important feature of our device. We have both relay wave and love wave resonance in the same device. By using love wave as the main measurement signal, and by using the relay wave, we use it for this purpose, for the surface coverage. Because the relay wave is very sensitive to the liquid contact. The energy will attenuate very quick to the surface liquid contact. So by calculate the amplitude of the relay wave resonance, we can know how much of the surface have been covered by the liquid. I will do a real demonstration here. For example, if I put a tiny drop on top of the surface in the propagation area. I put it on. You can see it tell us 28% of the surface have been covered, and also you can see the amplitude here. This first one is the relay wave resonance. The amplitude have been reduced to around 30% compared to the orange one. So now if I increase the liquid to big or drop, you can see the relay wave resonance peak have been totally disappeared, and it told 76% have been occupied. No, it's 84% have been occupied. So it's almost fully occupied on the propagation area. From now on, the relay wave have been disappeared. We can't use it as a measurement signal. But the love wave, you can see it here. It's still very robust. The resonance peak is still very high. So we use the love wave for measuring the antigen antibody in the liquid rather than the relay wave. We can see it from here. Since the relay wave disappear, we can see the love wave. It also is still doing the measurement. you can see the orange position is here. Now this peak is actually caused by the temperature change, but very quick it recovered to the real measurement signal. We can see it here. So this step from here to here, it shows the surface mass change of the device, which is if we put an antigen and an antibody on it, which tell us how many antigens have been bonded to the antibody. Now if we remove the liquid, you can see from the log wave resonance signal here, we can see the liquid have been removed, and also the surface coverage told us the liquid have been removed from the surface. We use the tissues to clean it thoroughly. Then we can see a further recovery of the surface. So for this specific device, we can see after the log wave fully recovered, the relay wave amplitude still didn't 100% recovered. That means this device have some dust on the surface because it's not always in a clean environment. It needs a deep cleaning. Now we also demonstrate another feature of the relay wave response to the mass change. The feature is the relay wave is only sensitive to the surface, how big the surface have been covered. It doesn't matter how thick is the liquid. So we are demonstrating this by just simply blowing some air onto the device surface. Let's see what's the response for the water evaporation onto the surface. Now we can see just by blowing air, the relay wave resonance peak have been disappeared, and the surface coverage is almost 90% covered. Now, by the condensed water evaporate, the resonance amplitude of the relay wave resonance peak have been increased. Then the surface coverage also reduced back. So this is a good improvement for relay waves energy. It's very easy to be absorbed to the liquid, which we can use it for the surface coverage analysis as we showed before, and also it can be used for the micro pumping, which is very important for the microfluidic like cell separation or some other applications. So until now we showed the relay wave is good for the surface coverage analysis and the micro pumping application, and the log wave because it's during the mass change of the surface, it doesn't have any amplitude attenuation, but it shows dramatic phase change. So the log wave is good for the mass change analysis for very thin